A good physicist, as they say, does most of their best work before they turn 30. And that's not the case with geology. Geology is a cumulative science, and so we learn a lot every single day that we work, usually. And there's some tidbits you just have to tuck away. And so it helps to have a good memory as a geologist. So one of the things that we always have to remember is rocks. And so rocks are going to be what most of you are going to be paid to identify in your careers, whether they're little tiny chips or in a core, or whether they're pieces of soils and sediments and so forth. And so you're going to have to be able to identify these earth materials. And so rocks you've already been introduced to in Principles of Geology, the beginning field course, or the beginning courses anyway, of geology. I'm assuming you haven't had very many field courses yet, so but hopefully you will get a chance to go on a field trip, but I'm not sure that this semester is going to look all that fruitful for any sort of outdoors endeavors. So we will do a small outdoor field trip, however, on campus, just to see some of the geology of the building materials on campus, and so you'll get to see that. Now, the other thing to keep in mind here, of course, is that geologists have this cumulative understanding. So what I'm going to do is I'm going to give you a short presentation on the rocks that we carry in our Geology 110 lab sets. And so I'll just give you a very quick overview with a few pictures of those rocks. We're not going to actually do the tests, but I will tell you what those tests are to identify the rocks, and also the minerals too, for that matter. So with that, I'll leave you, and thanks. Talk to you later. Yep. Well, there's a few things just before we get going here. Number one, what are minerals? Minerals are naturally occurring inorganic solids that have a crystalline form and a distinctive chemical formula. So those are the 5 points of what it takes to be a mineral. You should probably remember that from Geology 110. So that's what minerals are. There's about 4,000 of them. You know that there are different classes of minerals. You know that there are oxides. You know that there are carbonates. You know that there are sulfides, sulfates, sulfites. And so you're going to be taking probably mineralogy while you're taking this course. So I'm not going to dwell too much on the mineralogy here. For the rocks, you're going to be taking a course called petrology and also sedimentary geology at some point too. And so you'll learn in petrology, you'll learn the igneous and metamorphic rocks, and so you'll learn a much more sophisticated way to identify the rocks we're going to talk about today in this little short review. So for sedimentary rocks, we'll go into those in a little bit of detail, but you'll see those more in sedimentary geology as well. So I guess that's the little bit of introduction I wanted to give you before we start talking about granite. So for instance, with a granite, we're going to be looking at things that have quartz in them. We're going to have either plagioclase or orthoclase feldspars, or case spars we like to call them, or potassium feldspars. And you can also include microcline and a bunch of other sorts of, there's more feldspars than you can shake a stick at in mineralogy, and you'll get to find that out. So, and then maybe some accessory minerals, maybe some biotite, maybe some gabbro, and a few other sort of like dark minerals that would be intermixed in the granite, perhaps. Now, you should probably also recall when we talk about igneous rocks, we talked about felsic, intermediate, mafic, and then ultramafic. Those are the 4 categories, essentially, of igneous rocks. And then we have a whole series of textures by which we identify them. And the textures tell us about what type of environment they formed in, whether they were formed deep inside of the earth or whether they formed as extrusives at the Earth's surface. So those are things we're going to do with this little traipsing through the memories that you have of Geology 110 and your understanding of igneous, metamorphic, and sedimentary rocks. So with that, I'll go right directly to a lecture, I guess, right? A lecture review, that is. And this is all for lab number 2, essentially. And so anyway, I'll get on with it then. Thanks. Bye. So this is an entire row of granite right here. On the left-hand side, you can see that there's case bar, and that the the quartz that's in it's been described as being greasy looking, if you will. So broken quartz, as you know, doesn't have any cleavage planes on it. It just has a conchoidal fracture, right? And so it doesn't form nice flat planes or anything like that. And very commonly in granite, it's going to have that sort of gray color to it. So it's going to be translucent in this case, and then also the almost gray in this case. And then it's going to have that greasy sort of texture across the top. In contrast to that, the case bar, as well as many of the accessory minerals, and I think that's biotite on this one, certainly biotite on the second sample there, that you have, they tend to have fairly nice cleavage planes in which you can identify them with the hand lens, or you can identify them in thin section. So what you're looking at here are a pink granite, and then there's a white granite. And then if you go on to the third sample here, it's a granite porphyry. And what makes it a porphyry is there are large K-spar phenocrysts in this. And these phenocrysts are euhedral. Euhedral means that they have a good shape to them, I guess you could say, or true shape to them. And so those are slightly larger. And so that's what makes this a porphyry. It tells us that, in fact, that it had 2 stages of cooling. Okay, so what about the cooling in each one of these, in fact? So when we see a texture, a rock texture, where we can actually see the large crystals in it like this, and we know that it's igneous, for instance, so when we see those large crystals like that, we call it phaneritic. So phaneritic is this idea that the crystals are visible to the naked eye. So you don't even need a hand lens to be able to see the crystals, in other words. And so for the second one, it's the same as the first one. And the third one, of course, because of the 2 sizes, we call it a porphyritic texture. And some people refer to it actually as phaneritic, porphyritic in this case, because both sets of crystals, the large crystals and the large phenocrysts, in other words, and the smaller phenocrysts, actually they're not phenocrysts, the smaller crystals are all visible to the naked eye. And so all 3 of those would have formed inside of the earth, and that's why we call it granite. So that would be an intrusive rock. These are rocks that cool very slowly inside of the earth. They're insulated, essentially, when they intrude into either sedimentary rock or metamorphic rock or other igneous rock, for that matter. And so the porphyry, the 2 stages of cooling, would imply that perhaps it was associated with volcanism above this sort of like Pluton. And if you have a volcano, oftentimes you let off pressure, and when you let off pressure, sometimes you can go backwards along Bowen's reaction series, and then you can get the case bar perhaps in that sort of situation like that. In fact, this case bar has what they call zoned crystals in it in here, and so although the case bar may have began to form first at the very end of that, perhaps when an eruption could have occurred, you get what they call a Rapakivi texture to it, and so what you get, in fact, is a sort of reverse gradient. So you get coats or surroundings with plagioclase feldspar. So the principal minerals you see here, sample number 1, you get case bar and quartz and some accessory minerals, probably biotite, but there may be some hornblende in there. I don't have the sample in front of me right now. But then the second one, of course, is going to be plagioclase feldspar. One of the lighter ones, probably like albite or one of the lighter versions of the potassium of the plagioclase feldspars. And then there's some quartz in that as well, and that's going to have the gray color. And if you've got, they're slightly smaller than the crystals in the first sample there, but they're the ones that indicate that, that was the last thing that formed in that magma chamber. It's the last mineral that would have formed in that sort of setting. So there you have granite, and granite porphyry cooling deep inside of the earth, and one of them may be associated with volcanics above the Pluton there. In the next slide, you can see the equivalent of granite in the extrusive form, if you will. You have such fine crystals in this, in fact, that when it erupted, you don't even see the crystals. And so, in other words, you'd have to get a thin section of this in order to see the crystals. Thin sections, we grind it very, very flat, and then you polish it, and then you mount it on a glass slide, and then you cut the back of it off. We call it a billet, and so you cut the back of the billet off, and then you sand. sand it, but you grind it down and then you polish it again. So we get it down to about 30 thousandths of an inch, 30 microns. And you can look through the minerals and determine what the minerals are that way, very commonly anyway. And so that's an example of rhyolite. And so rhyolite is another felsic rock. So all the ones that we saw on the first slide, the whole 3 samples of granite were, of course, felsic, and this is felsic as well. And then you see in the second sample, here's another rhyolite. And rhyolite, of course, the volcanic equivalent of the intrusive rock, so it's the extrusive rock. Because we can't see the crystals, we assume that the cooling was so rapid, in fact, that you don't get big crystals to form. But the second one actually has some larger crystals in it, and so because of that, it actually has a texture we refer to as porphyritic, obviously, right? But some people refer to it then as aphanitic porphyritic. In other words, the ground mass, that is the minerals that are so fine that you can't see them, surrounding the larger phenocrysts in that, would have cooled very, very rapidly. And so those are that is a rhyolite porphyry. And so it's a porphyry as well. Just like the granite has the same composition roughly. It has feldspars and quartz and things like that in there, but in fact you can't see the crystals very easily. And so they call that material that's in between the phenocrysts, they call that ground mass. One word, Groundmass. So, and then the last one, of course, is tuff. And tuff is not only felsic also in this case anyway. It erupted again from, because it has this sort of aphanitic texture. You can't really see the minerals, but it's also fragmentary, and you can see chunks of rock in it. So they're not well-formed crystals, but they're chunks of rock. And so very commonly tuff is going to have a sort of a lightish feel to it. In this case, it actually has pieces of pumice and maybe even a little bit of obsidian in there. And so that volcanic tuff, as we would call it, or a tuff here, very commonly they're air-laid or they're water-laid. And so sometimes they're even, they're what they call welded tuffs, where they're so hot when they erupt and then finally come to rest. And of course, these are extrusive sort of rocks. So it's that gray area that's in between sedimentary rocks and igneous rocks. We still call them igneous rocks because they are out of a volcano, essentially. But when it erupts very violently, you get things like volcanic tuff. So that's a volcanic tuff. That's the first 6 samples there. Number 7 is pumice, of course. Pumice is an eruptive material as well, felsic in composition generally. And it has lots of porosity in it. And so, in fact, you could put a piece of pumice in water and oftentimes it will float until it becomes waterlogged and then falls. So that is pumice. It's a volcanic rock. But, again, with felsic composition. So, and oftentimes, in fact, it's actually made out of glass. And so it doesn't have any minerals in it so much as it has spun glass, essentially. It's kind of like... what do they make taffy that way, saltwater taffy, and it's so airy and everything. So it's got that sort of like spun crystals or in it. They're not really crystals, spun fibers of glass. In number 8 here, that's a granite pegmatite. And what makes a pegmatite actually is generally the water composition. And pegmatites very commonly are the last things that form out of a magma. And you get these sort of voids that may be present in a large body as it's cooling. And so the granite pegmatite, in this case anyway, probably form less, and you get these huge crystals in it. And oftentimes there's a connection to water in some way. So some of these crystals in pegmatites can be 100 feet long, maybe a little bit more than that actually in some cases. There's, for instance, in the Black Hills in the... I think it's a Harney Peak granite. There is the potential for having I think it was like 8 meter long crystal of spodumene. So it's just astonishing. This one does have some granite in it, or some potassium feldspar. It also has some probably some pelagic clay feldspar in there as well. There's quartz. And then there's all these accessory minerals that are in there as well. And I'm not sure. I think those are hornblende in that one. Okay, so everything we've seen so far has been felsic. The last one here is not. And you can still see the crystals in it, obviously, right? So it has that sort of phaneritic texture. But in fact, it's intermediate composition. So it gives you a good idea of the sort of color, really. So color is kind of important when it comes to looking at the mineral composition within igneous rocks. And so the light-colored rocks, the ones that are tan, the ones that are pink, the ones that are red, most of those, almost all of them, in fact, are felsic in composition. And they're going to be rich in the plagioclases and rich in quartz. Now, for the intermediate rocks, they're usually not very rich in quartz at all, if any is in there. So, in fact, what you get instead are a lot of plagioclase feldspars, in this case probably like a labradorite or bitonite, and you can actually see the gray in that is not quartz, and so it actually has cleavage planes if you were to get a hand lens on it. And I encourage you to get a hand lens for this course. We will be looking at some rocks in lab, obviously, here, so get a hand lens, and so you'll be able to see these crystals up close and personal that way. And so the darker minerals, of course, are what we again call accessory minerals, and that's going to consist of hornblends and pyroxenes and things like that. But that's an intermediate composition here. It's called diorite. For the next slide here, we have an andesite porphyry. Andesite is the equivalent of diorite, except it is the volcanic equivalent. And in this case, you can see some of the crystals, plagioclase crystals, that were preserved in that rock with a ground mass of even darker material, right? And so the andesite, again, a intermediate rock, intermediate composition, it's going to have a sort of gray-green sort of color to it. And then, in this case, lighter colored plagioclase minerals in this case, and probably it looks more like albite in that. So, anyway, that's andesite porphyry. It would be an extrusive rock, and so andesite, of course, is named for the Andes Mountains in South America. The next rock that you see here, next rock sample, is gabbro. And a lot of people call this black granite, in fact, because it has something in common with granite. It is very crystalline, obviously, and it has a lot of plagioclase feldspar in it. It's not going to have any quartz in it. Very seldom are you going to have quartz in it. So with a gabbro like this, you can see that it cooled very, very slowly and, over a long period of time, perhaps. So gabbros, in fact, are the kind of rock that you would expect to find in ocean crust. And so ocean crust very commonly has layered gabbros that make up parts of the lower crust in the oceans. Next to that, so if that's the intrusive rock, okay, it's a phaneritic rock. Okay, so let's go over this one more time. So andesite porphyry has a ground mass that is aphanitic and not phaneritic. Okay, the parts that you can see there are the phenocrysts, and so they are the exception to the formation of that rock. And so what's in between that ground mass is aphanitic. So that has to be an extrusive rock. The next one, of course, gabbro, is phaneritic, and that implies that it, of course, is an intrusive rock and very slowly cooled. And so the third one then is equivalent to gabbro, but it's the extrusive equivalent. It's so fine-grained, in fact, that you can't see the crystals in it. Now, you and I have already talked about this already. Now, I'm pretty sure that that sample is actually not basalt. It's probably a micro gabbro, but it looks just like basalt, or basalt, as they say in Britain. So, and in fact, elsewhere, you might even hear it called trap rock. And so that's the mafic and aphanitic equivalent of the phaneritic and mafic rock that is gabbro. The next in this succession here, that's a vesicular basalt. There's no doubt that that's not a diabase, in fact. So that is a basalt, a true basalt right there. And it's got bubbles preserved in it. So it was pretty close probably to the outer part of that volcanic flow. Most basalts flow out of very gentle volcanoes, usually. Gentle in the sense that they usually don't explode very, very violently. They can and have, but usually in steam eruptions where you get steam eruptions, if you have a mixing of groundwater and hot lavas that are in a volcanic neck perhaps, they can explode. And they leave behind explosion craters called Mars. And so, but that one is not. That one's actually from a flow right here, and you can actually see the bubbles, so indicating that you're pretty close to the edge or the outside or in the crust of that basaltic flow. So basalt, again, aphanitic texture, and you can see bubbles in it. So that's the vesicles, or the holes, the bubbles, if you will, in it. So vesicular basalt. Obsidian is unusual. It looks as though it should be a mafic rock, but it's not. It's actually got a composition that is felsic in this case. There are glasses, and you know that obsidian is that one that's the glass. It didn't have time to form crystals, well-formed crystals. It is an extrusive rock. It's a rock that would have come out of volcanoes like Newberry Crater, perhaps in Oregon, or you might see it coming out of Yellowstone National Park. They have felsic rocks that have this sort of same texture, and so very commonly obsidian is black like this. In Hawaii, there's a black glass as well, and of course those are mafic rocks there, and it's called Pele's hair there. It's not usually formed in flows and things like that, because usually that's what happens with the basalts. But Pele's hair, in fact, is usually associated with more violent sort of like activity in some of these basaltic eruptions. And the glass actually gets strung behind, and so you get these long strands of glass. But it is a glass, and so it's not what people generally call obsidian. They would call it Pele's hair in that case. But here's an obsidian right here. Sometimes you get impurities in it. And snowflake obsidian is one of those. Snowflake obsidian is where you get some devitrification. In other words, it changes the glass. Given enough time, even in a solid state like this, some of that glass can actually go and become mineral material, and so you can get snowflake obsidian. If you have some other impurities in it, like iron or things like that, you can actually get what they call mahogany obsidian as well. Okay, so the next one then is an ultramafic rock. It has that green sort of color. So we've gone from reds and pinks and tans and whites and all of those sort of like things that you would find in a felsic rock, and to the intermediate ones, which are more like medium gray or medium gray-green, and then you get into the mafic rocks, and they're typically black like this. And then lastly, you get into the ultramafic rocks, and they tend to be sort of greenish in color, and that's because of the content of olivine in there. And so olivine is the green mineral that you would see in dunite here. So dunite, or peridotite, some people call it, is a rock that's almost exclusively made out of olivine. So that is an ultramafic rock. That's the sort of rock that we expect to find in the mantle, okay? So if we find felsic and intermediate rocks in the Earth's continental crusts, we typically find the basalts in the ocean crust in the gabbros, and then we would find in the mantle dunites, dunite like this, or peridotite. So peridot is the gem version of olivine, and so that's why they call it peridotite. But it's got that beautiful sort of yellow-green color. And so on the next slide, that was the end of the igneous rocks. We're now in sedimentary rocks, because remember that sedimentary rocks form from the weathering of other rocks, right? And so you form sediments, and then they come together, and then they get cemented together or compacted. And in this case, actually, that's a chert breccia up on the upper left-hand side. And what broke those rocks all to pieces, and that's the chert was existing before this, right? And so there is a matrix. Matrix is the material surrounding those clasts. So we're not calling these phenocrysts anymore, because this isn't an igneous rock. This is a sedimentary rock. So it's one that was deposited in a certain sedimentary environment at the Earth's surface or near the Earth's surface. And so in this case, that breccia had to have some sort of event that broke those pieces together. I'm pretty sure that actually came out of the Tri-State Mining District right there. And so that rock is probably a result of ore mineral emplacement in the lead zinc belts that were in the northeast Oklahoma, southwestern Missouri, southeastern Kansas sort of area, the tri-state area as they call it there. And then the next one, the next rock here, is actually a conglomerate. And the way to tell a conglomerate from a breccia, it has nothing to do with the composition of the clasts. It has everything to do with how rounded the clasts are. So now we call these things clasts rather than phenocrysts. So clast is the pieces. And in fact, if they're smaller than 2 millimeters, we call them grains. And so grains are anything up to 2 millimeters. If you get beyond that, like a sand grain, right? And so if you get beyond 2 millimeters, you're going to call it a clast. And so the next one is in fact made out of grains of rock, but they're mostly feldspars and a little bit of quartz in there. And that's called an arkose. It's a type of sandstone. So if we went through the types of sedimentary rock, if you've got large clasts in something, it's either going to be a breccia or conglomerate. And if you have smaller grains in the rock, it's going to fall into the sand size category, and arkose is one of those sandstones. And so arkose is usually derived from the weathering of a granite. So if you have a granite and you're pretty close to it and you weather the grains out, if you transport these things, it's going to knock off the sharp edges off of those grains. And those grains will come to rest at some point and become cemented together, very commonly with quartz and quartz cements. And so the cement sticks it all together, perhaps. So that arkose right there is a feldspathic sandstone. Feldspathic refers to the feldspar content within that sandstone. The next one is a quartz sandstone. Now, obviously, you can't feel it. You can't. But the first thing that you would want to do with any of these rocks, in fact, would be to drop a little bit of dilute hydrochloric acid on it to see if there's any carbonate content, because carbonate's going to react with the acid and it'll cause it to fizz a little bit, right? And so very commonly when you see a sandstone, just to make doubly sure it's not a type of sandy limestone or something like that, you'll want to drop a little bit of acid on it and you see if it fizzes or not. If it does fizz, it probably has a little tiny bit of carbonate in it, or maybe a lot for that matter. So that is a variety there that's made exclusively out of quartz grains. And one of the things that defines sand grains, as well as every other clast is the word again, right? So clastic rocks are the ones that are made out of fragments of other rocks. Clasts are larger than 2 millimeters. Grains are smaller than 2 millimeters. This has a lot of sand grains in it. We call it a quartz sandstone. The other term, because we can't leave these things alone, essentially, if we're a geologist, we have to invent terms, right? Well, we don't do that in the more recent times here, but about 70 years ago, somebody referred to this as an arenite. And because it sounds better than sandstone, apparently, because there's so many varieties of sandstone, if it comes right down to it. But a quartz arenite would, in fact, be something that's almost exclusively made out of quartz grains, as opposed to having some mud in it, perhaps. The next one has mud in it, right? And so that is a wacky. And so if it were almost exclusively quartz with some mud in it, he would call it a quartz wacky. So quartz arenite and quartz wacky right there are the more common terms that a polished sedimentologist or stratigrapher would call these rocks. For the average run-of-the-mill geologist, you're going to call them both sandstones, but if it's a dirty sandstone like that middle sample is there, you're going to call that a gray wacky. So that takes us through 3 types of sandstone. How can you mix mud with sand grains like that? Well, very commonly gray wackies are found in deep marine sediments. Deep, but still above ocean floor, but near coastlines perhaps. And so these are things that would accumulate in toe of slope or on the slopes of continents. And so you weather the sand out of igneous rock somewhere on the continent from the source area, we call it, and you deliver it out to the oceans. And then the beaches, of course, are going to be well washed, and you're going to wash all that mud out of there. But in deep water, you may get some, shales deposited or clay minerals deposited out there. And every once in a while, if you're close to a submarine canyon, you can actually cause mass wasting events. Submarine landslides and things like that are going to generate a mixture then of the sand and shale and silt and so forth, and you're going to get a gray wacky. And so that's the origin of gray wackies very commonly. They're very commonly associated with deep marine sedimentation, where you get a mixing of fine grain and more coarse grain sort of sediments. The next one is the actual shale, right? So shale is made out of clay mostly. It can have some silt in it as well. Now, one of the things we do in geology is we eat rocks, and so, we don't really eat them, but we nibble on them. And when you nibble on these things, you find out what the clay content is, and you find out if there's any silt in it. The silt is going to scratch your teeth very, very slightly. And you'll feel that, if you don't have false teeth, you'll feel it anyway to see if there's something that was scratchy in that rock that you were nibbling on. And that's a gray shale here. And it has a fair amount of clay in it, as I recall, but there may be a little bit of silt in that as well. So what makes it shale? Otherwise, it would be called a mud rock. Mud rock is a term we use for rocks that are made out of mud. Shale, specifically, has been compacted, dewatered, if you will, right? So you squeeze it and squeeze it and squeeze it. All the water gets pushed out of the way. And then the shale itself gets a sort of alignment of the clay minerals that are in it, and you get little flat layers, essentially. And so shale tends to have a property we call fissility, Fissility, fissility. So in other words, it's fissile, and that's splittable, if you will. Fissilable material, they talk about that when you build atomic bombs and things like that, right? So fissile means ability to split things. So fissionable material, right? So fissile is that property. So that's gray shale there. You can see a black shale is the next sample here. This is... I'm losing track of what numbers these are, but black shale right up there. And you can see that the only difference between gray shale and black shale is the organic content. And the organic content could be as low as like 5% in order to give a shale a dark color like that. But the key thing to remember about black shales, that's the number one petroleum resource in North America right now. We used to refer to these as petroleum source rocks, but now as a black shale, that's the target that people try to drill in now, and they frack it, and then they try to keep the pore spaces open with sand grains in order to increase the porosity, and then you pressurize it, and you break it all to pieces, and so the oil then flows out of this rock. Some of it's always trapped within the rock, and flows into that pore space up the borehole. And you can produce oil and gas out of this. And in the old days, people used to use vertical drilling, and you would look for the petroleum reservoir. Well, the petroleum reservoir is typically in a carbonate rock or a sandstone or conglomerate. And you would get maybe a 30, 40, 60-foot pay interval. With the black shale targets, you can actually get up to a mile or even up to a mile and a half or 2 miles pay zone. When they do the horizontal drilling. And so there's a lot more oil to be had in that sort of like new model. They call them unconventional reservoirs, okay? So there's a lot of money to be had in the earth. So this is, that's an economically important rock right there. The next one has some economic importance as well, but it's chert. So if you ever do any kayaking, canoeing in the Ozarks here, you'll recognize chert as the rock that's in all the streams around here, and it's in many of the carbonate rocks. It is like the limestones and the dolomites in the Ozarks, and we're loaded with those, right? And so when you weather away or dissolve the limestones and you form karst topography, and same with the dolomite, when you dissolve it all away, the chert gets left behind because it's made out of cryptocrystalline quartz. So chert made out of cryptocrystalline quartz is going to be kind of the survivor mineral. If it's the last thing that crystallizes out of a magma, it's going to be the last thing that actually weathers away too. So it's funny how that works. So it's very, very resistant to weathering. So that is a piece of banded chert there in the middle section there. And it's going to scratch glass, right? You're going to be able to scratch glass with it, and it won't fizz, right? The next one is gypsum. Gypsum is that mineral that defines hardness of 2 and Mohs scale. And so gypsum, we use it for wallboard, plaster of Paris, things like that. It's used for a lot of chemical preparations. So it's CaSO4.2H2O. If you drive the water off of it, you can get it to and crush it. You can turn it into plaster of Paris. You add the water back to it, and it's going to form a mold, if you will, or cast. You can do casting material that way. So gypsum is very important, very useful mineral for humanity. We can make drywall out of it. Other things that are very handy for that, It absorbs sound, so that's kind of a neat property for it as well. And there's a few different, gypsum's a mineral, right? But it's also what we refer to as an evaporite mineral. So it occurs in vast quantities, usually wherever it seems to be. And so when they mine this, very commonly you're mining the rock, so this is another one of those interesting rocks that you can just call it gypsum. Don't call it gypsum rock or rock gypsum or anything like that. Just call it gypsum.
It's 22 hours.
So the next slide gives us an idea of another economic mineral from the side view and from the top view here. That's coal. Coal's made of compressed plant debris. And so if you take plant debris and you bury it without oxygen, anoxic environment essentially, and so you bury it, you cut off the oxygen, things stop decaying essentially then. And then you compress it, and then you turn some of those lipids and the proteins and the carbohydrates and so forth. And they get simpler and simpler as you begin to bury it. And so as you bury it, you drive off the volatiles first, and you drive off the water too. And then eventually you're just left with carbon then. So it's a process called carbonization or coalification. And so with fossils, we call it carbonization of plant debris perhaps. But coalification for turning material that originally was probably like a peat material, that is organic rich, roots, leaves, bark, and so forth, resins, that material, once it gets compressed, will turn into something like this, compressed and also coalified. So the next one is the siltstone, and there's a little bit of dolomite in it as well. It's a local rock around here. You can see some wormholes in it there. This is one that's going to be finer than sand. Okay, so it's a little bit finer than sand, and it's the next size down. So if we had a conglomerate, then you could have a sandstone, and then you'd have a siltstone next. And then the finer materials that are made out of clay and the mudstones, for instance, the shales and mudstones will be the next category down in grain size. So silt's that fine area between what's mud and what is sand. So every once in a while you get thick accumulations of that. Not real commonly, however. The next one is a limestone. Limestone is a marine rock typically, although you can get some freshwater limestone very occasionally, but they're not usually preserved for very long anyway. So that is a marine limestone. It's a local rock around here. We call it the Burlington Keokuk limestone. It's very fossiliferous. It's loaded with crinoid fossils, ossicles we call them. When you put dilute hydrochloric acid on this, it's going to fizz like crazy. The next sample here you see is also a fossiliferous limestone, and you can see the fossils in it much more easily. And so you see little tiny fossils. I think it's a piece of a trilobite even there. And so you get chunks, bryozoans perhaps in here as well. And if you don't know what those are, you're going to find out soon enough. Okay, so I think that's the next lab we're going to deal with here. So if that is what a limestone looks like, and the first one is a fossiliferous limestone, and the second one's a fossiliferous limestone. In other words, it's a limestone that has fossils in it, okay? So you're going to learn different terms to describe these later on. For instance, in stratigraphy, you're going to learn some terms that will be much more appropriately used for describing these rocks. But for now, just call it a limestone if it fizzes very, very vigorously. The last one fizzes too. It's actually layered, however, and it's the sort of rock that you might find in a cave or something like that. It's almost like a speleothem. It also forms in places like on waterfalls and things like that. That's a type of rock called travertine, so it's banded. In Mexico, they call that onyx, and so onyx can take a high polish and makes beautiful statues and things like that, and so that's a type of limestone as well. But it's a chemical precipitate in this case. If the other two were deposited in oceans, that one was deposited on dry land. And so the next one is an oolytic limestone, is what they typically called it in Geology 110. It's actually ooidal limestone. Ooids are the little tiny round things, the little tiny BBs in there. They're about the sand grain size, and they're layered like one layer on the outside, another layer like a bunch of pearls or something like that. They form naturally in the oceans where there's a lot of wave activity and enough carbonate to make them precipitate on these coatings like that. So I don't know if you know what a jawbreaker is, right? So if you've ever had a jawbreaker and you finally get it down small enough and you crunch on it, you can see it's got layer after layer after layer of candy in it, right? Well, don't do that with this, but you do have the same kind of layering in there. So kind of like tangential radial growth of these little tiny particles, and they get washed around in the ocean, and then they accumulate in sandbars, essentially. Places like the Bahamas, very commonly you get that. In the Persian Gulf, another common place to get that sort of sedimentary rock. The next one is a rock that's made out of nothing, almost exclusively out of seashells, and that's why it has so much porosity in it. We call it a coquina. It's so loaded with fossils, and so it's a limestone made almost exclusively out of fossils. And the fossils themselves are made out of carbonate, right? And so that's things like bivalves and snails and all sorts of other sorts of creatures that make up this sort of coquina. And in this case, we don't say that they're made out, we say they're made out of carbonate, but it's not like actually calcite. Well, it may be calcite, but it's a biomineral. And also you could also have a mineral in there that's called aragonite as well. Okay, the next one is chalk, and chalk is also made out of fossils, believe it or not. Not the bits that you can see there that are sticking out so much, but the actual grains they're so fine it takes a scanning electron microscope to see them, but they're actually coccoliths or coccolithospheres that break apart. They're a type of algae, and that algae can then break apart in the oceans, of course, and you form chalk. And so chalk is the rock we were talking about when we talked about the Cretaceous. So that was the age of chalk, essentially. So you find chalk all around the world. You find it in Kansas. You find it in the Paris Basin. You find it in the White Cliffs of Dover. So that is a chalk right there, made out of coccoliths or coccolithospheres. The next one, here's another limestone. It looks a lot like a chert, doesn't it? But you drop acid on it, it's going to fizz, right? You try to scratch glass with it, it won't scratch because calcite has a hardness of 3, not a hardness of 6, or a hardness of 7, like chert or quartz does. So that is a limestone there. It's going to fizz, as we said before, quite vigorously. The next sample will not fizz quite so vigorously. They look almost identical, don't they? Well, they're both made out of mud, essentially. So one's made out of lime mud and the other one's made out of dolomitic mud. So dolomite will fizz, but not quite so vigorously as what limestone is. And in fact, in the old days, they used to refer to dolomite as magnesian limestone. So it's a mixture of calcium and magnesium to form that rock. And so you get part calcium, part magnesium, and then you get CaCO3 beyond that, 2 of those. So that's what dolomite and the dolomite formula, chemical formula is. So the next one, we're on into the metamorphic rocks. It looks like a conglomerate, sort of, and it's one where the grains, the clasts have all been crushed together, essentially. You may get embayed clasts, but it's one that has been altered, and so the alteration, we call it metamorphism. There's regional metamorphism, and then there's also contact metamorphism. When you get a metaconglomerate, typically it's going to be regional metamorphism. And we've already talked about a metaconglomerate too. In fact, we talked about that with the Jack Hills conglomerate, metaconglomerate, right? So that's a metaconglomerate right there. Not from the Jack Hills, however. The next one is a quartzite. It looks a lot like a quartz sandstone, except again, the grains have been kind of crushed together, if you will. And now when you break this rock, it's going to break through the grains rather than around the grains like a typical sandstone does. So it's more dense, in fact, than most sandstones. And so sandstones, if they break apart very easily, we call them friable. When you get into quartzites like this, unlikely that you're going to have any friable quartzites. They're a little bit harder. Still, again, you're going to scratch glass with that quartzite. The next sample looks a little bit like a white version of the quartzite, except if you were to drop acid on it, you would find that it fizzes. It's made out of calcium carbonate. That's the mineral composition. And in fact, the rock itself is marble. Marble was used for a lot of different things in the geologic past, and the human past for that matter, right? So most of the statues that were made in Rome, most of the statues that were made in ancient Greece, they were made out of marble. When you find a good source for marble, they used it for all sorts of carving like that. And it's easy to work, right? It has a hardness of 3 as opposed to quartzite, which has a hardness of 7. So marble reacts with acid. Now, each one of these rocks, and it's easy to figure out what the rock was, the parent rock, if you will, for the metamorphic rock, metaconglomerate. It used to be a conglomerate. For the quartzite, it used to be a quartz sandstone. For the marble, it used to be a limestone. So that's the parent rock for each one of those 3. Slate looks a lot like the black shale that we looked at earlier, except it's a little bit more dense. And in fact, it has what we call slaty cleavage. It actually has natural planes that are flat, completely flat in this case. And its hardness is a little bit more than what a shale is. And so if you were to tap it on a desk, you would hear it actually make a noise, kind of. So that's more phonerous, I guess you could say. But it is a type of rock that still has a lot of uses, right? So in Britain, they used to use, well, all over Europe, in fact, they used slates in order to make roofing materials for houses, right? It's very durable. And then you can make pool tables out of it, right? So a 3/4-inch slate pool table is kind of like the standard, I think. You can get a 1-inch slate pool table and pay a lot more money for it. A schist would be the next grade up from a slate. If you took slate and you pressurized it, there's actually an intermediate rock that's not shown here called phyllite. Phyllite tends to have a sort of sheen to it, if you will, and so does schist for that matter. And this schist, in fact, has garnets in it. And so if you metamorphose a rock, you bury it very, very deeply. And usually this is, again, going to be a regional sort of metamorphic product here, but a garnet schist is very commonly something that people can map. We talked about mapping along the boundary fault. It's the Highland boundary fault in Scotland, right? And so in the Grampian Highland part, not the islands and highlands in the far west out there, but in the Grampian Highlands, they had zones that they could map in this. Well, they can also map zones in the New England area of the United States. They were once connected, in fact, so it was kind of easy to see how you can get the same zones, maybe even in the New England area that you might see in Scotland. The next rock is probably one of the easier ones that you recognize. It's nice. It has mafic and felsic bands in it. There tends to be a segregation of the minerals. When you get under enough pressure, it's a high-grade metamorphic rock. So you would go from low-grade to intermediate grade to a high-grade metamorphic rock with this succession from slate to schist to gneiss. That's called metamorphic grade. So the last 2 to talk about, and I'm not a specialist on this by any means, but there seems to be some amphibole if you're going to have an amphibolite, right? And so hornfels is also a mixture. So one's like a salt and pepper rock, and the other one looks like it. If it were an igneous rock, you would say that it was mafic, okay? And I'm not good enough to be able to spot and tell you what's an amphibolite and what is a gabbro, unless you're dealing with like regional sort of mapping and things like that. It's like, oh yeah, well, it's easy to tell you're in a metamorphic terrain as opposed to an igneous terrain. So that's the easy way to tell it apart, I guess. Hornfels, you get a lot more of the plagioclase in there that gives it that sort of salt and pepper look. Now that's taken us through igneous rocks, sedimentary rocks, and now metamorphic rocks. And so that's just a sampling of what we have at Missouri State University. Those are the sort of rocks that we have our Geology 110 students become familiar with and able to identify. And so you should remember these, I guess is what I'd say. So that's why we did this little 45-minute apparently rock review. But anyway, thanks for your attention, and we'll go on from here and do some more stuff. So talk to you later. Bye now.